Okay, so what we're going to do today is we're going to find the values of some trigonometric functions of new angles. Last time we talked about how to evaluate sine, cosine, and tangent for certain nice angles. For example, we considered, as a motivating example yesterday, sine of 270 degrees. And remember that the new definition of the sine function is the following. Well, you begin by drawing your angle, 270 degrees, in standard position, which means that you put the initial side here along the positive x-axis. 270 degrees would be 3/4 of a turn, so the terminal side would wind up right here. You then draw a circle of technically any radius, but for convenience we always choose the radius to be 1. So we draw a circle of radius 1, and then we look at the point of intersection between the terminal side of this angle and the circle that we've drawn. And whatever the x and y coordinates are of that point, these are the two values which are used to define the three trig functions. So sine, for example, is defined to be y over r being the radius of your circle. Now, since we drew a circle of radius 1, that's really just y over 1, which is y. So the sine of 270 is just the y coordinate of this intersection point. Now, what is this intersection point? Well, because this is a circle of radius 1, and this little length right here is a 1, we see that the coordinates of this point must be 0, -1. And therefore, sine of 270 is -1. That's the y coordinate. Now, that's pretty easy because this point right here lies on one of the axes. It lies on the y-axis, and it's pretty easy to work out what the coordinates of that intersection point are. On the other hand, if I pick an angle which is not on one of the axes, that is not 90 or 180 or 270 or 0, it's a little less obvious how to find the coordinates of this point. And today we're going to talk about how to find the coordinates of the intersection point for some other angles. So let's just start by considering 45 degrees. So let's suppose that I want to find, the sine, the cosine, and the tangent of 45 degrees. Well, of course, what I have to do is I have to begin by constructing my angle in standard position. 45 degrees looks like this, right? And then I draw my circle of radius 1. And in order to find the sine, cosine, and tangent of 45 degrees, I have to determine the x and y coordinates of that intersection point. Now, it's a lot less obvious what the coordinates of this point actually are. And to find them, we have to do a bit of geometry. So here's the trick for finding 45 degrees. We begin by dropping a perpendicular line from that point of intersection down to the x-axis. So this is a perpendicular line. We now have a right triangle. So, of course, this angle right here is 45 degrees by construction. Now, if you think about it, this angle is 45, that angle is 90 degrees, which means since the three of these things have to add up to 180, this angle here also has to be 45 degrees, because the angles have to add up to 180. Now, if you like, this is a 45, 45, 90 triangle. You don't have to remember your special triangles necessarily. What you should remember is that anytime two angles are equal or congruent inside of a triangle, the opposite sides are also congruent. In other words, because this angle is congruent to that angle, this side is congruent to that side. We can use that information to find the lengths of these sides of the triangle. Because after all, remember that this side right here is a radius. It's going from the center of the circle to the circumference. This was a unit circle, a circle of radius 1, which means that the length of this hypotenuse has to be 1. Now, I don't know what the length of this side of the triangle or the length of that side of the triangle is, but I'll just call them both x because they are the same. Now, if I apply the Pythagorean theorem, what do I obtain? It says that this side squared, so x squared, plus this side squared, that's x squared again, has to be equal to 1 squared. Okay? X squared plus x squared is really 2x squared, and of course 1 squared is just 1. Well, we can then solve this equation for x. we find x squared is equal to 1/2. And now if we take the square root of both sides, we have x is equal to plus or minus square root of 1/2. Now, if you remember our exponents and logarithms unit, you might remember how to simplify an expression like that. Taking the square root of a fraction really means you just take the square root of the top and the bottom of the fraction. But then, of course, the numerator, root 1, is really just 1. So we have plus or minus 1 over root 2. And then I would argue that this expression is still not simplified because we have a root in the denominator. We have to rationalize denominators. And if you figure how that goes, you have to multiply top and bottom of the fraction by the root appearing in the denominator. So when we do that, we obtain plus or minus, let's see, 1 times root 2 is, of course, just root 2. And then in the denominator, we have root 2 times root 2, which is just 2. So I find that x is either positive or negative root 2 over 2. It's not positive or negative. It's really one or the other, if you think about it. Because 45 degrees sits in this quadrant, it's pretty obvious that this distance here, I mean, it's positive, right? I mean, I suppose x represents for us this distance, the length of this side, which should be positive. So it's actually positive root 2 over 2. So that's the length of x, right? So this distance here is root 2 over 2, and this distance here is also root 2 over 2. If you think about it, that means that the coordinates of this point here are both root 2 over 2. Both the x and the y coordinates are root 2 over 2 because, this distance here, that's really going to give you your x coordinate, and then this distance here is really going to give you your y coordinate, and both of those distances are root 2 over 2. So that's the coordinates of the intersection point for 45 degrees, and that allows us to compute sine, cosine, and tangent of 45 degrees. For example, the sine of 45 degrees is going to be, well, it's technically y over r, but since r is 1, it's really just the y coordinate, which is root 2 over 2, as we saw. And the cosine of 45, technically it's x over r, but r is 1, so that's really just x, which again is root 2 over 2. As far as tangent is concerned, tangent is defined as y over x. I suppose that would give us root 2 over 2 over root 2 over 2. You can simplify this by doing some complicated keep it, change it, flip it stuff, like taking one fraction and dividing by another fraction is the same thing as multiplying by the reciprocal. Or you can just recognize that, hey, how's it going? Or you can just recognize that the numerator and denominator of this big fraction are equal, and so therefore this whole thing is really just 1. So the tangent of 45 is 1. Okay, so we're now going to do exactly what we just did, but with a different angle. Let's consider 30 degrees, or if you like, pi over 6 in radians. So my objective is to find the sine, cosine, and tangent of this angle. So how do we do it? We begin by drawing the angle in standard position, like always. So maybe 30 degrees looks something like this. It's a bit smaller than 45. We construct our circle of radius 1. That's the unit circle. And then we look at the intersection point of the terminal side of the angle with our circle. So that's this point right here. And of course, this point has some coordinates, x comma y, and really what we have to do is find those coordinates. Once we know those, we can compute sine, cosine, and tangent of the angle. So how do we do it? Well, like usual, we drop a perpendicular line from the point down to the x-axis. So that makes a right angle. Now, this angle here, by construction, is 30 degrees. And this angle, of course, by construction, is 90. Which means that this angle here must be 60 degrees, because the interior angles have to add up to 180. Now, what I'm going to do next is a bit strange. I'm actually going to reflect this right triangle across the x-axis. So if I reflect this right triangle across the x-axis, then I'll get something like this. So I sort of reflect the entire picture this way. Okay? Now, this angle here, that is the smaller angle, is also going to be 30 degrees. And this angle down here, of course, is going to be congruent to this one, so this angle here is 60 degrees. Now what I want you to do is look at this larger triangle that I've constructed. This angle is 60 degrees, this angle is 60 degrees, and it's obvious that this angle here is 60 degrees. Therefore, the larger triangle here has all of its angles congruent. And if you remember from geometry, there's a theorem that says when that occurs, when all three angles are 60 degrees, all three sides are also congruent. In other words, this side is congruent to this side, is congruent to this whole side here. They're all congruent. Now, why is that useful? Because we actually know how long this side is. It's a radius. It's going from the center of the circle out to the circle itself. So that's a radius. And this was a unit circle, so the length of this side of the triangle is 1. But because each of these sides are congruent, it follows that the other sides are also 1. In other words, this entire side here is also length 1. Now, if you think about it, this side here, which is one of the sides of our original triangle, this side right here must be half of the entire side here, and half of 1 is, of course, 1/2. If you think about it, that tells us that the y-coordinate of this point is 1/2, because the y-coordinate is the height of this point above the x-axis, which is exactly the same thing as the length of this segment. All that remains is to find the x-coordinate, which can be found by determining the length of this side of the triangle here. Let's call it x. And now let's use the Pythagorean theorem on this triangle here. It's a right triangle, so what can I say? This side squared plus this side squared has to be equal to this side squared. So in other words, x squared plus quantity 1/2 squared has to be equal to 1 squared. So this tells me that x squared plus 1/4 is equal to 1. And subtracting 1/4 yields x squared is equal to 3/4. And now I can take the square root of both sides and find that x is equal to square root of 3/4. Technically, I should put a plus or minus here, but in the context of the problem, it's clear that x is a positive value. The x-coordinate of this point is a positive number. This expression can be simplified. When you take the square root of a fraction, you just apply the root to the top and the bottom. So that's root 3 over root 4, which produces root 3/2. So that's the x-coordinate of this point. So in summary, the coordinates of this intersection point on the unit circle are root 3/2, comma 1/2. And now that we know the x and y coordinates of this point, we can evaluate the basic trig functions at pi/6, or 30 degrees. So for example, the sine of 30 is, well, it's technically y over r, but since r is 1 in this case, that's really just the y-coordinate of this point, and we just saw the y-coordinate is 1/2. Therefore, sine of 30 is 1/2. What's the cosine of 30? Well, once again, technically that's x over r, but since r is 1 here, that's really just x, and therefore the cosine of 30 is just the x-coordinate of this point, which is root 3/2. And as far as the tangent is concerned, let's actually compute that since it requires a little bit of work. Of course, the tangent of 30, the definition is y over x. So the y-coordinate of the intersection point that we just found was 1/2, and the x-coordinate was root 3/2, so let's plug those in. So 1/2 and root 3/2. To simplify this expression, you should think of this as one fraction divided by another fraction, and you might remember that means you sort of keep the first fraction, but then you change the division to multiplication, and you flip the second fraction upside down. In other words, dividing by a fraction means multiplying by its reciprocal. Something nice happens here. The 2's cancel, and we're left with 1 over root 3. But for whatever reason, we've all decided that we're not supposed to have square roots in denominators, so I have to rationalize this denominator and get rid of the root 3. That means I have to multiply top and bottom by the square root. So in the numerator, I have 1 times root 3. That's just root 3. And in the denominator, I have root 3 times root 3, which is just 3. So that is the tangent of 30 degrees. Okay, so that is the derivation of sine, cosine, and tangent for 30 degrees. And I want to point out now that even though I've technically only done 2 angles, 45 and 30, from these angles I can actually determine the sine, cosine, and tangent of many other angles, basically by using symmetry. Okay, so now what I would like to do is go to our blank unit circle here and fill in some of the information that we've just found. You've done this before. We've got a spot for the measure of each of these angles in degrees, and then we've got a spot for their measure in radians. What is new here is that every point associated with each angle has a blank space for the x and y coordinates of each point. And, previously we sort of knew some of these coordinates, right? Before today we knew that the coordinates of this point, this is 0 degrees or 0 radians, it's the same thing in both measures. The coordinates of this point are 1, 0. Because it's a unit circle, radius 1, so this point is 1 unit over and none up. And similarly, we know that the coordinates of this point were 0, 1. That would be pi over 2 in radians. But now we're in a position to fill in some of these other spots. So let's go ahead and do that. The first one we did today was 45 degrees, which measured in radians is pi over 4. Now, what were the coordinates of that point? If you remember, it was root 2 over 2 and root 2 over 2. And then we just did 30 degrees, which in radians is pi over 6. And we found that the coordinates of that point were root 3 over 2, comma 1/2. Now, I claim that we actually have all we need to fill in the rest of the unit circle. We're kind of done doing calculations. I want to start by figuring out this point right here. That's 60 degrees, or in radians, pi over 3. What are the coordinates of that point? Well, you can derive them in a very similar way that we derived them for 30, but there's actually a clever way of getting the coordinates. Just notice that this point right here, whose coordinates we're trying to find, is, it can be obtained by reflecting this point here, the point associated with 30 degrees, across this diagonal line. This line here, the line, the terminal side associated with 45 degrees, is the diagonal line y equals x. If you reflect this point across that line, sort of like mirror image, if you reflect this point across that line, then of course you get this point. Now, if you remember from geometry, reflecting across this diagonal line actually just interchanges the x and y coordinates. It switches them around. So from that argument, we know that the coordinates of this point are the same as this one, but with the x and y coordinates reversed. So this must be 1/2, comma, root 3 over 2. Now, the rest of the unit circle can be filled in by using basically symmetry arguments. So if you look at this point right here, for example, which is 2 pi over 3, the coordinates of this point, compare that with the coordinates for pi over 3. They're very similar. If you look, the y coordinates are the same, right? The height is the same. As far as the x coordinate is concerned, the distance from the middle of the, from the y-axis is the same, except the x coordinate here should be negative. So the coordinates of this point will be the same as the coordinates of this one, just with the x coordinate negative. So that's going to be negative 1/2, comma, root 3 over 2. Now, a similar argument can be made for all of these angles. As a matter of fact, every single pi over 3 angle will have essentially these coordinates, except with some sign differences. One or both of the coordinates might be negative. So pi over 3, 2 pi over 3, The next one is 4 pi over 3, which is this one down here. So 4 pi over 3 is down here. This coordinate, the coordinates here are going to be the same as the coordinates of 2 pi over 3 and pi over 3, except that the both of the x and y coordinates will be negative because 4 pi over 3 is in this quadrant. And that's actually true for all the angles, and it's one of the advantages of measuring things in radians. If you look at this pi over 4 angle here, every other pi over 4 angle, that is 3 pi over 4, which is here, that would be 5 pi over 4, which is down here, and 7 pi over 4. Every pi over 4 angle has exactly the same coordinates, except that some of the coordinates might be negative depending upon the quadrant in which the angle lies. So that allows you to and the same thing is true for all the pi over 6 angles, and the same thing is true for all the pi over 3 angles. So that allows you to quickly fill in the rest of the unit circle by symmetry. And one more comment, we computed the value of tangent for a couple of these angles. I think we computed it for both pi over 4 and pi over 6. Excuse me. We found that the tangent for pi over 4 was 1. So the tangent of pi over 4, we found that to be 1. And we also looked at the tangent of this angle, tangent of pi over 6, and we found it to be root 3 over 3. You can pretty quickly calculate the tangent values for every other angle on the unit circle, again by basically making symmetry arguments. Let's start here at pi over 3. Well, notice that the coordinates of pi over 3 are the same as those for pi over 6. The only difference is that the coordinates are switched around. Now, the tangent function is defined as y over x, right? So if you go from pi over 6 to pi over 3, you are simply switching the x and y coordinates. That means that if you go from here to here, all that's going to happen is you're going to obtain the reciprocal of this guy right here. So the tangent value of pi over 3 must be the reciprocal of the tangent value of root 3 over 3, so that's 3 over root 3. Of course, that can be rationalized. If you multiply top and bottom by root 3, then you get 3 root 3 over 3. But then this 3 cancels with this one, and you just get root 3. So the value of tangent here at pi over 3 is just root 3. Now, at any rate, you can figure out the tangent values of every other angle pretty quickly. So, for example, how can we do it? Well, let's think about the tangent value for 2 pi over 3. Again, tangent is y over x. And comparing these two coordinates, the y's and x's are basically the same. The only difference is over here, the x coordinate is negative. So you're going to get basically the same thing, root 3, except, if you think about y over x, if one of the coordinates is negative, as it is here, then y over x is going to be negative, right? If y is positive and x is negative, then that fraction, y over x, is going to be negative. So this guy is going to be negative root 3, right? And then very similarly, if you go down to the pi over 3 angle down here, this angle, of course, this angle sits in the 4th quadrant. Both the x and the y coordinates will be negative. So if you have y over x where both y and x are negative, the resulting fraction will be positive, which means that the tangent of this angle must be positive root 3. And you can sort of make a similar argument to find all the tangent values as you go around. Okay, and tomorrow we'll talk about how to sort of remember all of this.